In electron beam welding, the coalescence heat is generated by the kinetic energy of a focused stream of electrons directed upon the joint. The electrons are produced by an electron gun, accelerated to high velocity, shaped into a beam by electrical fields, and then further collimated or made parallel and focused by an electromagnetic lens. This electron stream is developed in high vacuum, but actual welding can be performed in either high vacuum, partial vacuum, or standard atmospheric pressure. Because of the intense and concentrated heat generated, total heat input is low, minimizing heat-affected zone size and part distortion. This also allows for the creation of extremely deep and narrow welds. Additionally, joints inaccessible by other welding processes can be welded. Virtually all ferrous and non-ferrous metals, thin or thick, can be joined. Welding speeds are fast, and filler metal is not generally required. Equipment cost for electron beam welding is typically high, and welding is generally limited to machined parts assembled in primarily butt, corner, and lap joints.
Aluminium heat sinks for commuter trains are joined using electron beam welding.
Electron beam welding is an advanced method for joining metal parts. The technology has been used at the Institute since 1964. Nowadays it's being developed by the third-generation researchers of the Electron Technology Group. The electron beam welding machine consists of two main sections, electronics and physical section. The physical section consists of the vacuum working chamber with the pumping system, the manipulator and the electron gun as the electron beam source. One part of the electronic section is a high-voltage power supply to accelerate the electrons. The welded parts are placed in the working chamber and the inner space is evacuated. The electron beam is focused onto the surface of the welded workpiece and the weld is formed by mutual movement. Welding is usually performed without any additional material. The combination of the deflection system and the computer can be used to display the workpiece in the electron microscope mode, to weld along complex paths, or to create seemingly multiple beams for multi-pool welding. The deflection system is also used for engraving and local heat treatment of the surface layer, or in 3D printing using selective melting. A typical feature of electron beam welding is so-called deep penetration effect. Power density of the electron beam reaches such values that the beam penetrates the material very rapidly. Thanks to this, the weld acquires its typical knife-like shape, even for very deep welds. Vacuum as a protective atmosphere, the depth effect, welding of high-temperature materials and reactive metals, and high productivity predetermine electron beam welding for applications in nuclear and automotive industries, in aeronautics and space exploration. The Institute uses electron beam welding in construction of vacuum and cryogenic systems for research projects. Under the contracted research, the technology is available to 50 cooperating industrial partners as well. The long-term research of the electron beam welding technology resulted in an agreement on development of a welding machine with a foreign partner.
We are living in the era of great changes. The power of the human mind has made our life more comfortable, shortened distances, and opened up new horizons. But for the global industry, our era is the time of great challenges. The airplane is the fastest and most expensive means of transport. Since the advent of the first aircraft, designers have been working to reduce its weight and make it more reliable, and so reduce the cost of each kilogram carried by air. Nuclear power is the most promising and cheapest way of generating electric power. However, each structural element of a nuclear reactor operates under conditions of overload and ultra-high temperatures. Extension of their service life and enhancement of their reliability and safety are the main tasks for engineers. Thus, technical progress is impossible without new materials and their new unique properties: ultra-lightness, ultra-strength, and heat resistance. However, the introduction of new materials requires new progressive techniques of their connection. For over 70 years, this field of research has been developed here at the Patton Research Institute of Electric Welding. The institute was founded in 1934. It employs 3,500 staff. The Patton Institute has sold more than 150 licenses to the United States, Germany, Japan, Russia, Sweden, France, China, and other countries worldwide. Structurally, the institute comprises an experimental design and engineering bureau, pilot production facilities, 3 pilot plants, and more than a dozen engineering centers. The technologies developed by the Patton Institute have served as prerequisites for successful implementation of many audacious global projects, such as forced gasification across the USSR, the world's most powerful weapon, the Satan ballistic missile, continuous welded rail tracks allowing trains to move at 500 km per hour, semi-automatic underwater welding, and welding in the outer space. Notably, the Patton Institute was one of the originators of electron beam welding, the technology without which nuclear power engineering and modern aircraft, rocket and engine building industries would be impossible. How does it work? Electrons are focused into a tight beam and accelerated to ultra-high speeds. When they hit the surface, their kinetic energy is converted into heat, and so metal is heated to high temperatures. As a result, the weld is characterized by large depth and small width. Electron beam welding ensures reliable connection of refractory, chemically active and dissimilar steels, as well as high-strength aluminum and titanium-based alloys. Unlike arc welding, this method reduces energy consumption by 10 to 15 times and the fusion area by 25 times. Electron beam welding has no alternative if post-welding heat treatment of products is impossible, if welding deformations should be minimal, and for a range of thick-walled and thick-plate structures of critical applications. Making the most of its powerful scientific potential, the Patton Institute develops unique technologies with due regard for individual customers' requirements. Here are just a few examples. The engine is the heart of an aircraft. The manufacturers that offer more economical and more powerful engines win the market. The hotter the gas fed to the turbine, the better these parameters. For this reason, joint connections have to withstand extremely high temperatures. In 2014, Patton scientists developed a method to weld the outer part of the casing of the aircraft engine's front intermediate pressure compressor. The customer was Motor Siege, one of the world's leading engine manufacturers. The material was VT5L lithium alloy. Previously, the unit had a cast design, which resulted in high production costs and unstable quality. The developers faced 2 problems while making the welded structure. 1. Geometrically, the joint was a variable cross-section. 2. The through penetration weld had to be 5 to 25 mm thick and made in one run. Scientists of the Patton Institute found effective solutions to both problems. The process is entirely controlled by special software, and the welding program excludes an operator. The welding factor of joints conforms to the strength factor of the metal body. The main part of an aircraft engine turbine, the rotating blade, bears the brunt of the heat. The engine's operation fully depends on its strength. And this is about flight safety. The Patton Institute has developed a method to restore damaged blades by welding in triangular inserts. The customer was Motor Siege, and the material was VT titanium alloy. One rotating blade costs tens of thousands of euros, and an engine has a multitude of them. Our technology provides for the service life extension of this part by several times. The economic effect is obvious. Currently, a pilot batch of restored blades is undergoing strength tests. After their completion, the method will be applied at the customer's production facilities. We have developed an electron beam welding method for high-pressure spherical balloons of aircraft. The customer is the Space Agency of the Republic of India, and the material is VT6 titanium alloy. As compared with argon arc welding, this method minimizes welding deformations, post-welding mechanical treatment, and weld spatter inside a spherical balloon. Experts believe that the future of the aerospace industry belongs to magnesium alloys, one of the lightest and at the same time one of the most durable types of materials. However, The introduction of magnesium alloys on a large scale has so far been hindered by imperfect connection techniques. The Patton Institute has developed a hybrid technique for connecting this material. The first stage is friction welding, and the next stage is electron beam welding. Thanks to pretreatment of welded edges by stir friction, cracks and other defects are avoided, and welded joints become almost twice stronger, with their plasticity and impact resistance enhanced as well. This technology has been developed for rehabilitation of intermediate casings of aircraft engines by welding in a 6 mm thick rectangular insert in the damaged area. One of the most challenging aspects of the global energy industry is reliable connection of thick-walled structures like walls of a nuclear reactor. At present, walls thicker than 40 mm are connected by a multi-layer weld, which sometimes takes up to 100 runs. This technique requires multi-step preparation and significantly increases the likelihood of weld defects, which subsequently affects quality and performance. The Patton Institute has developed a new technique to solve this problem. The customer is the Russian public holding company Izhorsky Zavody, the only CIS manufacturer of equipment for reactors of the so-termed nuclear island, as well as for reactors of the petrochemical industry. The material is chrome molybdenum steels. Owing to 90 kilowatt beam power, materials up to 200 mm thick can be welded together in one run. This is a unique achievement, yet unsurpassed by any manufacturer of welding equipment. Comprehensive studies have confirmed that the weld is as strong as the metal body. Using this method, the customer is able to skip several preparatory stages and cut the time of welding by several times, thus significantly improving weld joint quality and increasing productivity. A heat exchange unit is the key element of a nuclear reactor. Because of colossal pressure in the tubes reaching 10 megapascals, water does not boil at 270 degrees centigrade. High radiation adds to the most extreme wear conditions. The Patton Institute has developed an electron beam welding method to connect the heat exchanger walls with multiple tubes. Unlike traditional argon arc welding, this method doubles the penetration depth and the unit's service life. The welding proceeds automatically according to a preset program. This method has been successfully applied in the construction of nuclear-powered vessels. The energy crisis forces humankind to search for and develop new oil and gas fields, and here the main task for engineers is to extend the service life of drill bits. They consist of 3 vertical case segments made from medium alloy high-strength steel. The traditional method of successive welds did not allow for the regular geometric shape of the drilling bit. As a result, its service life and performance characteristics reduced. The Patton Institute has developed a method of simultaneous 3-joint welding by 3 guns. As a result, output capacity has increased to 5 items per hour. Using this method, the customers have not only increased their outputs by several times, but have also increased considerably the end product's economic efficiency. This technology has been successfully applied at Chinese factories for more than 5 years, allowing them to put out products with higher added value. Scientists of the Patton Institute have developed a slab connection method for the metallurgical industry. The customers, a pool of integrated iron and steel works in China, needed to increase the thickness of their slabs from 20 to 40 millimeters. However, they were limited by the rolling mill's capacity. Traditional welding methods did not allow them to obtain homogeneous material because of cavities with air forming inside. Electron beam welding takes place in vacuum. At the same time, penetration is 5 times deeper than in arc welding. This ensures homogeneity of metal during subsequent rolling and the output capacity of 1 item per hour. The Patton Institute successfully applies combined electron beam scanning, wave, circular, etc. This helps to avoid uneven heating and ripple of molten metal. As a result, weld depth fluctuations are reduced from 25% to 2%, and welds have no cavities. The Patton Institute has been developing and manufacturing electron beam welding equipment since the 1960s. What are the unique advantages of our equipment? Our welding units have the smallest guns in the world, so firstly they weigh less, and secondly the gun moves faster, increasing the unit's efficiency. The welding electron beam is monitored and controlled by the raster joint tracking system. The gun reads the weld geometry, even the most complex one, like an electronic microscope, and converts the obtained data into a mathematical model. The human factor is excluded completely. At the second stage, raster analyzes how the material behaves during welding. The system scans the weld additionally and adjusts the beam trajectory. Over the last 10 years alone, 57 electron beam welding units with chamber volume from 0.5 to 100 cubic meters have been put into operation. The Institute's customers are such leading machine builders as Boeing, Hitachi, Mitsubishi, Airbus, Turboatom, Motor Siege, Zariamash Project, and others. So what's the secret of the Patton team? It is a unique scientific school, high-tech production facilities, focus on global projects, persistence, and unprecedented revolutionism.